let's put this Fourier thing to work. Let's do an example of a sloped string. Let's see. So this would be the case where you have your string shape bound over here and bound over here, and you just have it going up at a constant slope, but then it pulls all the way back down to 0. Okay. Like that. So mathematically, we would just think of that as a line, right? It's just a line where the slope has some value, or we'll just call it c for a constant. And we would describe the shape part of this function as a height y, where this is the origin of the y-axis, and we have the axis here for x, where we'll call this the origin. So it's clamped at 0, and we'll continue to call this part L. Clamped at 0 and L, it's just being shaped into a constant slope that goes all the way back down. So let's see. So then our function y equals cx from x equals 0 to x equals L. That's the function we're going to describe with our Fourier series. So we know that what we can do is say that this y of x can be described as a sum of an infinite number of sinusoids. So we're going to use an, and they are the harmonics n pi over L x. And we have to find the an's, where an's are equal to 2 over L times the integral from 0 to L. And I'll go ahead and plug it in. We know that what you put here is the actual shape of the function, so I'll put cx, right? Cx sine n pi over L x dx, like that. So now, if we can just solve that integral, we have our an's, and then we have created this series that if you put in infinite terms, it actually will go from here all the way straight down to there. Okay? So this is a tricky integral. So the way I learned to do integrals is you think, well, I could integrate that, but if I take the derivative of this with respect to x, then there's nothing to cancel this x, it doesn't go away. It depends on how you do them in your head, but you can see that's not a trivial integral to do. So what we're going to do is integrate by parts. This is not a calculus class, but I do remind you of the things you need for common physics problems. And when you're doing a Fourier series like this, you often need to integrate by parts. So remember, and I'm going to read my notes here, that when you integrate by parts, if you have an integral that you can describe from a to b as a function of one f of x, some function, times a derivative of a function, g of x dx, then that's equal to the functions f of x times g of x, that evaluated from a to b, minus the integral from a to b of, let's see, f prime of x, g of x dx. Right? Just some little trick from calculus you learned. I'm sure they proved it in your calculus course, and I'm sure we've all forgotten the proof. Okay, so now we're going to use it. So it's useful when you have, usually when you have the integral of something where you have one function that's easy to get the integral of, and one function that's easy to get the derivative of. Okay? And that's what we have here. I can't integrate this whole thing, but I can integrate sine x to get to L over n pi cosine, or negative, and then I can take the derivative of just x, and that's just 1, right? So that's not so hard. But to do these, I have to be very careful. I always write out the whole thing. I remind myself, okay, f of x is going to be equal to x. We're actually going to pull the constant out. Therefore, f prime of x is equal to 1, right? That derivative is just 1. And then I say, okay, this is the g prime part. So g prime of x is equal to sine n pi over L x. Therefore, g of x, must be equal to, let's see, let's go minus, and then L over n pi cosine n pi over L x. So there I have my 4 parts, and now we can just write it down. The AN equals, let's see, 2 over L, but I'm pulling the C out, so that's 2C over L. Let's see, times the entire integration by parts. So f of x times g of x evaluated from a to b. So let's see, x times minus, times that part, so that's minus Lx over n pi cosine n pi over Lx. And that whole thing is evaluated from a to b, which is from 0 to L in this case. All right, and then minus the integral from a to b, which is 0 to L, of f prime of x, which is 1, times g of x, which again is minus L over n pi, so that minus will go there, L over n pi cosine n pi over Lx dx. And all that is times that, and we will keep going.